Let's take a look at some basic integration techniques, little things that you should be trying every time you go to integrate something. Now, I'm going to give you a list of things to try. These are kind of the order that you should approach them, but not necessarily. If you do recognize a way to do it, you can kind of skip past these. But these are all the things, well, not all the things, we're going to add to this list later. But these are the types of things you should be looking for when you're integrating. So let's go and start out with the super basic and work our way up. So of course, the very first thing you want to do when integrating is ask, well, can I integrate it? If you can integrate it directly, then you're done. So the very first thing I'm going to say is, can you integrate it directly? Like something like this, of course we can, right? That's, it's not that. It's 1/3 x cubed plus 3/2 x squared plus 4x plus c. And you're done. So directly is what you're always looking for first, is do I know how to integrate it? Now that doesn't mean that directly is necessarily easy. We could end up with something like, we're going to see a lot of variations on something like this, like x squared plus 25. And you say, well, what can I do here? If you're really practicing, you'd recognize, hey, this has a form that I know how to integrate. If I pull out that constant, this looks like our arctangent formula, which is the integral of 1 over, sometimes the books write these backwards, but a squared plus u squared du is 1 over a arc tan u over a plus c. And you can see that it fits this form. I mean, these are backwards, but you can see our a here would be 5 because that's squared. Our u here is x because that's what's being squared. And the derivative of x is dx. So this fits the arctangent formula exactly, which means we can just plug this into it. So 1 over a, which would be 1/5, arc tan of our u would be x over 5 plus c. As you see, we can integrate it directly just using a formula. So when it says directly, either you're just using one of your rules, or you can be using a formula, which a lot of times is like your arc trig formulas that you may run into. All right, that's the first thing you want to try. Let's just try a couple variations on something that looks like this. What if I said the integral of, change it slightly, 2x over x squared plus 25. Well, we want to integrate this directly, but I really don't see a form that it fits into. One of the first or second or third things, always directly is always first. But the second and third things are kind of, well, whatever you see. The next thing I want to say is, can I rewrite it or can I use a substitution? Now here, I'm actually going to put this down as a u du substitution in this case. And you can see if we let the denominator be u, x squared plus 25, the derivative of that is 2x dx, which is exactly what we have on the top. So this ends up being 1 over u, and all that's du. So log absolute value of u plus c, natural log of x squared plus 25 plus c. So our u substitution is an incredibly powerful integration technique. You want to make sure that you really got a good handle on that. Now, one of the small subtle things that you'll see in a textbook a lot of times, an author may write this without the absolute value and have parentheses around that, because we know that x squared plus 25 is always positive. So if you saw this in the back of the book and you have parentheses instead of absolute values and you're wondering why, if the author can determine if the stuff inside is always positive, most of the time they'll get rid of the absolute value, because technically speaking, it's a more simplified expression without the absolute value. At this stage though, if I were you, I'd always leave the absolute value on there just in case. All right, let's go back this way. So substitution, huge giant category of things, types of problems that you'll be able to integrate. What if I gave you, let's see, what about just the integral of x plus 3 squared dx? All right, if we were told to integrate this, again, you'd say, can I integrate it directly? And no. A u substitution would actually work here, and it would work here just fine, probably the way I would actually do it. But you could also say, you know what? I can multiply that out real easy. I know if I multiply that out, I get x squared plus 6x plus 9, which I can integrate directly. So another thing that you're going to want to be looking for very early on is rewriting. Because rewriting can really make things easy. And now notice, this would be like 1/3 x cubed plus 3x squared plus 9x plus c. Now again, this could very easily have been done with a u substitution or rewriting. So rewriting is, these two are kind of interchangeable. It's kind of whichever one you see first or the easiest out of the two. All right, let's try another one. Let's do one kind of like the one I'm erasing. What if I have x plus 3 over x squared plus 25? All right, so again, quite a bit like the one that we've done a couple of times now, because you kind of see the differences here. You'd say, well, really not seeing a way to integrate it directly. I really don't see a way to rewrite it. Remember these two are, maybe a u substitution would work. Well, the only choice we would have for a u substitution would let u be x squared plus 25. du would be 2x dx. Well, if I just had the x on the top, I could deal with this constant of the 2, but that plus 3 is really getting in the way. So, like a lot of things we do within life, let's do this. Since that 3 is in the way of me doing a substitution, let's kind of get rid of it for a second. Let's write this as x over x squared plus 25 and 3 over x squared plus 25. Right? This expression says everything on the top is divided by x squared plus 25. So I did x divided by x squared plus 25 and 3. Now the reason I did this is because this integral I know how to do. I may be stuck with that one here in a minute, but I know how to do this. Here if I let u be x squared plus 25, du would be 2x dx, which depending on how you learn how to do substitution, you may solve or just put the 2 in and the 1/2 out front. This ends up being 1/2 the integral of 1 over u du, natural log absolute value of u, and 1/2 natural log absolute value of x squared plus 25. Now notice I didn't write plus c yet because technically we still have another integral over here that's a piece of this. Now how do we integrate this? Well, again, this one's actually a directly one using a formula because I can pull the 3 out front and notice that this has the same form as the arc tangent. So like one of the earlier examples, this would be 3/5 arc tangent of x over 5 plus c, 3/5 arc tangent x over 5 plus c. And there we go. There's our result. So taking a problem that has a complicated numerator and breaking it apart by dividing the denominator into each one of the terms in the numerator might be helpful. So that is something you're going to want to look out for. All right, let's try another one again, somewhat like this form here. What if I have x squared over x squared plus 25? Okay, so again, you try to go through kind of all your steps here. Oh, by the way, let me go ahead and I didn't write down what this was. Kind of, I'm going to say breakup fractions. That's what we did on the last exam, kind of breakup fractions. All right, so if I'm looking at this one and I say, well, I don't know how to integrate this directly, maybe a u substitution. Again, about our only choice for a u substitution would be this denominator again, but du is 2x dx. Now I could handle the 2 being off, but I have an extra power of x on the top, and it doesn't look like that's going to be easy to deal with. So this is probably not going to work. However, rewriting, this kind of falls in the rewriting category, even though it's going to get its own tab down here in a second. When you have a rational expression, remember that's a fraction of polynomials, and the degree of the top is greater than or equal to the degree of the bottom, rational expression where the degree of the top is greater than or equal to the degree of the bottom can't write. Use long division first. All right, so this is going to go underneath our list of things to try, but this one's somewhat special because here we have to be talking about a rational expression for this generally to work. So, long division. So I guess we'll come back over here so we got a little bit more room to work with. So I need to do x squared plus 25 into x squared plus no x's plus nothing. All right, if you're struggling with how to do long division of polynomials, I'm sure somebody's put a video up about it. I know I have. You might want to go take a look at it. So what do I have to multiply x squared by to be x squared? That'd be 1 and distribute. So that's x squared plus 25 and subtract. There's nothing, so we get negative 25. Since the degree down here is lower than this degree, this will be minus 25 over x squared plus 25. Which means I can rewrite our integral, which started out as x squared over x squared plus 25 dx, as the integral of 1 minus 25 over x squared plus 25 dx. Now I'm going to basically end up with two integrals here, so just the integral of dx minus 25 the integral of x squared plus 25 dx. Now, it doesn't get much easier than integrating dx, and we've already done that second integral about 3 times today, because we've been working with just variations of a problem. So of course the first one is x minus, so remember this is 1 over a, arctan is u over a, our a is 5 and our u is x, so this is going to be 25 over 5, which is 5, arctan x over 5 plus c. Okay, so just kind of swinging that up to the top so we can see it a little bit better. So the integral of dx is x minus, we get 1/5 times 25, which is our 5, arctan of u over a, so x over 5 plus c. All right, so just another thing to watch out for when you're integrating. If you're dealing with a rational expression and the degree of the top is greater than or equal to the degree of the bottom, think about doing long division. All right, let's try another kind of category of problems. Oh, let's say I gave you this. All right, we're actually going to take a look at this problem 2 different ways. Neither one is better than the other, just a couple of different ways to think about it. When you're looking at this and you were told to integrate it, if we're kind of going down our list, I don't know what the answer is just by looking at it. Don't see a way to rewrite it or a substitution, because my only choice for a substitution would be 1 plus e to the x. So the derivative of that is e to the x dx, and I have nothing like that on the top. So substitution really wouldn't work the way that it is. Can't break up the fraction because I only have one thing in the numerator. Long division is not going to work because it's not a rational expression. So notice I'm out of ideas over here. Now the way that we're going to handle this is actually kind of weird. And here's what's the next thing you might want to try is multiplying by 1 or adding 0. And you're like, that's not going to be very helpful, because if you multiply by 1, it doesn't change anything. And if you add 0, it doesn't change anything. All right, of course, it's not going to be the actual number 1. It's going to be a special looking 1, and it's not actually going to be the number 0. It's going to be a expression that's actually 0. So let's start out with the first one. What if we multiply by 1? This is actually a fairly common integral that we see, and one way to do this is multiply the top and the bottom by the same exponential, but with an opposite sign of the exponent. So I'm going to multiply this by e to the negative x. Okay, so no, same exact exponent, just the opposite sign. So if this was 4x, we'd multiply by negative 4. If this was negative 5x, we'd multiply by 5x. Same exponent, but the opposite sign. Now the reason that this works is if you multiply on the top, of course, you get e to the negative x. On the bottom, when you distribute, you get e to the negative x, e to the x times e to the negative x. Here we're multiplying, we have like bases, we add those exponents, so that gives us e to the 0, which is just 1. Now, if you're looking at this, you'd say, oh great, you actually made it more complicated by writing it like that, except for now, a substitution will work, because now I got an exponential on top to help me. If I say, let u be the denominator again, du would be negative e to the negative x, which is almost exactly what I have on the top. So if you divide both sides by negative 1, and we do our substitution, now the negative is going to come out front. This is going to be 1 over u, and e to the x dx, e to the negative x dx is du, so this is 1 over u du, which is negative absolute value of u, and our u was right here, e to the negative x plus 1. Okay, so there's a valid answer for this problem, and there's nothing wrong with doing it that way, but there's actually another way that we can approach this as well. All right, so I'm just going to write our problem back up here. 1 over 1 plus e to the x dx. All right, the idea for this is kind of the same thing, but just looking at it through a different lens, so to speak. We know from our original expression, if we were going to use substitution, we did not have an exponential on the top to help us with that. So basically what I'm going to do on the top, I'm going to go 1 plus, I'm going to write the exponential I need, but then take it away. Now notice, what did I really add to the top? I added nothing, or 0. Now I'm actually going to use step, 4 over there, and I'm going to break this into 2 pieces. I'm going to break it into 1 plus e to the x over 1 plus e to the x dx minus, and then the e to the x that I needed for my substitution. Now, of course, all of that's just 1, so that's just the integral of dx. And over here, we would do a substitution. We let u be 1 plus e to the x, du is e to the x dx. So that's exactly the pieces we have here. So this is 1 over u du. Just for room's sake, I'm going to bring it up here. I'll leave that there just for a second. Okay, so the integral of dx is x minus the natural log of the absolute value of u plus c. Now in this case, our u was 1 plus e to the x. Okay, so there is another valid answer. Now this is the type of problems you're going to start running into the more and more you learn about things like integration. Is there may be more than one way to approach the problem. And if you did it one way and you look in the back of the book, it may have something that looks completely different than what you did, because you did a different technique. Now, are those 2 answers the same? Here's what I'd suggest you trying to do. See if you can use all your knowledge of properties of logarithms and see if you can prove that these 2 are exactly the same. I'm going to give you a hint. See if you can take this one, manipulate it, and turn it into this one. All right, so believe it or not, multiplying by 1 or adding 0 is a pretty helpful technique to learn how, or to change things so you can actually integrate them. Let's take a look at maybe one more quick technique. When I say quick, the example will be quick, but it's a huge category. Let's say if I had the integral of, let's do tangent squared. That'll work. Okay, so things to try. We want to try to directly integrate this. I don't know what the integral of tangent squared is. Really can't do a u to u substitution. I mean, we do have, technically that's the tangent inside a power, but if you let u be equal to the tangent of x, du is secant squared x dx, and we don't have anything like that, so that really wouldn't work. Rewriting. Now, again, technically this is going to be rewriting, but we're going to kind of skip past that for a second. We don't have any fractions, can't break it up. Long division, well, it's not a fraction, so that wouldn't work anyway. Multiplying by 1 or adding 0, I'm gonna put that on the back burner. Here's what I'm gonna do. It's like, you know what? I know with our trig functions, there's a lot of different identities we can use to just rearrange or rewrite them. And one of my trig identities is the Pythagorean identity, where I know sine squared plus cosine squared is equal to 1. Now by rearranging this, I can replace sines with cosines or cosines with sines. But remember, there are two other Pythagorean identities. Now if you don't have them memorized, here's an easy way to do it, because most people have this one memorized. If you take this expression and you divide through by sine squared, you get one of the other identities. And if you go divide through by cosine squared, you get the other one. So watch what I mean. I'm just going to point here. So if I divide through by sine squared over sine squared is 1. Cosine over sine is cotangent. Of course, that's going to be squared. And 1 over sine is cosecant. And again, it's squared. If I take this expression and if I divide through by cosine squared, sine over cosine would be tangent, of course it's squared. Cosine over cosine is 1. 1 over cosine squared would be secant squared. Okay, so you've got to know at least your main Pythagorean identity. It's helpful to remember these, but you got to at least remember how to get to them. Now, why would this be helpful? Well, if I were to replace tangent squared with what? Tangent squared would be what? Secant squared minus 1. Well, now I know how to integrate both of these directly, because I know what has the derivative of secant squared. That is just tangent. And the integral of 1 is x. So by rewriting this, so technically it is at step 3, by rewriting it using our trig identities, we were able to actually get it into a form where we could integrate this. All right, so watch out for your trig identities. If you don't see how to integrate it directly, rewriting it using one of those might be helpful. All right, this by no means is a complete list of things to try. We're going to add a whole bunch to this list, but these are things you should always be looking for when you are trying to integrate.